everyone! Welcome to part 2 of chapter 11. Last time we learned all about stoichiometry, which was calculating an amount of a product from a given amount of starting material. We did that calculation using a new conversion called the mole ratio. Today, we're going to use those stoichiometric calculations to do limiting reagent problems, and we're also going to be able to calculate percent yield. It's very important that you are super solid on all of the calculations that we learned last time before starting this lecture. If that's not true, make sure you go back and do some of those lecture worksheet problems to get the practice that you need in order to be able to do today's lecture. All right, let's go ahead and get started. Okay, so when we have chemical reactions that we're doing in lab, a lot of times we're not adding both of our components, like both of our reactants, in the same amount, in the same stoichiometric amount. One of them will usually be a limiting reagent. One of them is just going to be kind of in a small amount, and we're going to have a ton of extra of the other one. Usually this is for cost-related purposes. We want to have a small amount of our really expensive reagent, and we're going to have a very large amount of the one that's cheap, so that we make sure that all of the really expensive one reacts. This is usually what happens. Usually one of them is in a smaller amount than the other, and the one that's in the smaller amount is going to make a smaller amount of product. So we call this the limiting reagent. It's going to limit the amount of product that can be formed. Once we use up all of our limiting reagent, then it kind of stops making products, right? So thinking about this non-chemistry wise, if we were putting together a bike, so we would have, right now we have 8 wheels, we have 4 frames, and we have 3 pedal assemblies. And I want to know how many bicycles can I make? Okay, well in each bike, if you look, we're going to use 2 wheels, we're going to use 1 frame, and we're going to use 1 pedal assembly. Okay, so we can make 3 bicycles. We have enough wheels, right? We need to use 6 wheels, so we'll have 2 left over. We have enough frames. We only need 3 frames, and we had 4, so we'll have 1 left over. But we'll run out of pedal assemblies here, right? We only have 3 pedal assemblies, so we can only make 3 bikes. So in this example, our pedal assemblies were our limiting reagent. We ran out of them, so we can't make any more bikes. So the thing that's completely used up in our chemical reaction, that's the limiting reagent. And like I said here, that's the pedal assembly. The ones that we have extra of, right, like the frame and the wheels, those are called in excess. We have extra, we have an excess of those. So let's just talk about this even more simply. Let's say we were making peanut butter sandwiches. And it's not even peanut butter and jelly sandwiches. Like, we're just making peanut butter sandwiches. So I've got some bread and a jar of peanut butter. I have 8 slices of bread and 1 jar of peanut butter. Okay, how many sandwiches could I make? Well, if we think about this, in a sandwich, we need 2 pieces of bread and, I don't know, a few tablespoons of peanut butter, depending on, how peanut buttery you're feeling. But here, our limiting reagent would be our slices of bread. A jar of peanut butter is huge. You're definitely not going to use up a whole jar of peanut butter for 4 sandwiches. Or if you are, you're making your sandwiches wrong, right? So here, our limiting reagent is our bread. We can make 4 sandwiches from the 8 slices of bread, so that is our limiting reagent. And then the peanut butter is left over. Here it looks like we have about half a jar, depending on how much you like peanut butter. There's going to be some left though, right? And so our peanut butter is the one that's in excess. Alrighty, we're going to stop here and work together on the limiting reagents worksheet. This is different from our lecture worksheet. It's a whole separate thing, and part of today's lecture will be working through this together. So I'll kind of explain how to do a problem, you'll pause, you'll do it, and then we'll go over it. And that will be kind of embedded as we go through today's lecture to help really solidify this concept of limiting reagents. So what I want you to do now is go ahead and find the limiting reagents worksheet. We are going to complete example number 1. Just in case you don't have it in front of you, I'm going to also have it here in the slide. I would go ahead and recommend finding it though in the chapter 11 module. All right, let's do example number 1. So in example number 1, we are making stick figures. It says that each stick figure contains 4 parts. We need 2 legs, 2 arms, a torso, and a head to make one stick figure. So using this box below, I want you to draw as many stick figures as you can, but you can only use the parts provided in those boxes up above, okay? And then you can just draw the extra parts kind of in the empty space next to the box with a stick figure. So go ahead, pause here, and draw some stick figures. Alrighty, so what you should have realized is that the head is limiting. We only have one head, therefore we can only draw one stick figure. So there's my kind of sad attempt at a stick figure. Just remember, I'm really good at chemistry, just not so much at art. So I'm going to stick to chemistry from now on, I promise. But our leftover reagents, we have a leg left, we have 2 arms, and we have a torso. So all of the other components are in excess, but our head here would be our limiting reagent. All right, so our limiting reagent, here's a technical definition for you. It limits or it determines the amount of product that can be formed in a reaction. The reaction will only occur until our limiting reagent is all used up. Once it's all used up, it can't keep going because it can't make more product. Kind of like we couldn't make more stick figures because we ran out of heads. Our excess reagent will be the reactants that are not completely used up. There might be one excess reagent, there might be more than one. Kind of like in our stick figure example, we had leftover torsos and legs and arms. So in this reaction, this is the reaction of carbon and oxygen gas to make carbon dioxide. So again, usually what happens is one of our reagents is in excess and the other one is limiting. Here, because we had some leftover carbon, that's telling us that our carbon is our excess reagent. Therefore, the oxygen, which you can see, all of our oxygen got all used up in making carbon dioxide. Therefore, our oxygen was our limiting reagent here. Alrighty, let's go back to the limiting reagents worksheet. Now we are going to do example number 2. So again, I recommend you actually go and find the worksheet, but I do have it here in the slides if you don't have access to it. So this one says ammonia is composed of 2 different elements. So ammonia is NH3. This is a common name for nitrogen trihydride. So ammonia is made up of 1 atom of nitrogen and 3 atoms of hydrogen. And in the empty box, I want you to draw as many molecules of ammonia as possible using the atoms provided. Okay, so we have 3 different H2 molecules and 3 different N2 molecules. Okay, this is H2 here and N2 here. Remember, both of these are diatomic because they appear in Hofbrinkel, which is why you see them in the boxes as diatomic molecules. Okay, but I want you to draw as many ammonia molecules in that box as you can using only what's provided. Okay, after you do that, answer the 3 questions below. Then we'll go over it. Alrighty, so looking at this, we can make 2 ammonia molecules. Okay, because we only have 6 hydrogens and we need, so in NH3, we need 3 in each one, right? So that means we can only make 2 ammonia molecules. You know, each one will have 3 hydrogens for a total of 6. So when we do that, we use up 1 nitrogen in each one, meaning we actually have 4 nitrogen atoms or 2 diatomic molecules left over. So in this case, hydrogen was our limiting reagent because it limited the amount of ammonia that we could form, right? We had extra nitrogen, but we were limited by our number of hydrogen atoms. So since we had extra nitrogen, that says that element is in excess, okay? And it says how much excess? Well, we had 2 extra molecules of N2, or you could have said 4 atoms of nitrogen. Alrighty. Thinking about this, let's go ahead and complete page 2 of the limiting reagents worksheet. So we're going to just kind of keep going. So in this problem, what I want you to do is the same problem again, essentially, that we were just doing, but we're going to look at it a little bit differently. So in situation 1, it says totally ignore the amount of nitrogen present. So you can assume that we have as much nitrogen as we want. And it says, okay, just using the amount of hydrogen that you have here, how many ammonia molecules could you form? Remember, ammonia looks like this. You would have your, solid nitrogen, and then you would have your 3 hydrogens. So just thinking about the amount of hydrogen, how many ammonia molecules could we form? And then we're going to do the exact same thing, but with the nitrogen. So saying, okay, if we had as much hydrogen as we want, how many ammonia molecules could we draw from the amount of nitrogen there? All right, go ahead, pause here, give this a go, and then come back when you're ready to go over it. Okay, so if we say we have as much nitrogen as we want, and we're just limited by our hydrogen, then we can draw 2 ammonia molecules. This is because we started with 6 hydrogen atoms, and to make 1 ammonia molecule, we need 3 hydrogens, so we only have enough to make 2 ammonia molecules. If the opposite is true, and instead we say, okay, we are limited by our amount of nitrogen, and we have as much hydrogen as we want, then we can make 6 ammonia molecules, because we started with 6 nitrogen atoms. Each ammonia molecule, right, because ammonia is NH3, each ammonia molecule only needs 1 nitrogen. So if nitrogen was limiting, then we could make 6 ammonia molecules, 1 with each of those nitrogens. This is essentially a different way of thinking about how we did the previous problem. So in this first part, in situation 1, we said, okay, if hydrogen is our limiting reagent, how much ammonia could we make? And our answer was 2 ammonia molecules. And in our situation number 2, we said, okay, if nitrogen was limiting, how much ammonia could we make? And the answer was 6 ammonia molecules. So this is a different way of thinking about the same calculation that we were doing in the previous problem. But this is actually going to be really similar to the way we do this mathematically in chemistry. So looking at this, we can now answer these questions. It says, which reactant, hydrogen or nitrogen, produces fewer molecules of ammonia when it's completely used up by the reaction? So the one that produces fewer is hydrogen. So therefore, hydrogen is our limiting reactant or limiting reagent. Those terms are used interchangeably. So here our answer was hydrogen. And then it says which reactant, hydrogen or nitrogen, produces a greater number of ammonia molecules. So here our greater one was nitrogen. So this, right, nitrogen would be our excess reagent. Okay? This says when we look at the situation that produces a fewer number of ammonia molecules, how many of the excess reagent were used? Okay, so if we go and we look at the situation that produced the fewer number of ammonia molecules, so that would be the first one, we want to know how many atoms of the excess reagent were used. So in this situation, I want to know how many atoms of the excess reagent were used. So the answer here was we used 1, 2 nitrogens, right? That's how many of the excess reagent were used. So we used 2 nitrogen atoms. Okay. And so again, this says looking at the situation that produces a fewer number of ammonia molecules, how many atoms of the excess reagent were left over? So the way that we do this calculation, we say, okay, we had 6 nitrogen atoms initially, right? We used up 2 of the nitrogen atoms, making those ammonia molecules, and therefore we had 4 nitrogen atoms left over. Okay? Again, these calculations are going to be very similar to how we are going to do this mathematically. I just wanted to kind of explain it conceptually first so we have something to kind of ground it on when we go forward. All right, let's get back to chemistry. We are now going to do these same limiting reagent problems, but we're now going to use moles. Okay, so here's kind of a really common problem, or a really basic problem. This says when 4 moles of hydrogen is mixed with 2 moles of chlorine, how many moles of hydrochloric acid can we form? Okay, this should stand out to you as a reaction, and especially thinking about our last lecture, anytime we have a reaction, right, or we're doing some conversions, we're going to need a balanced chemical equation in order to do some mole ratios. All right, so our first step here would be to write an equation. We're going to have hydrogen mixing with chlorine to make hydrochloric acid. Okay, so this is a combination reaction. I have already given this to you, but from chapter 10, you should be able to write these reactions on your own. Okay. All right, so now let's go about solving this problem. This says when 4 moles of hydrogen is mixed with 2 moles of chlorine, how many moles of HCl can we form? So this is telling you, okay, in my flask, I put 4 moles of H2. And then I also put 2 moles of Cl2, and I want to know how much product can I make? Okay. So the way that we're going to do this is we are going to calculate the amount of product from each reactant. Okay, so these are going to be 2 separate calculations. You are going to do 2 train tracks for this problem. You're going to say, okay, if I start with hydrogen, how much hydrochloric acid can I make? Or if I start with chlorine, how much hydrochloric acid can I make? This is very similar to the problem we were just doing with nitrogen and hydrogen to make ammonia. We did 2 separate calculations to see how many ammonia molecules we could make. Same thing here. We're going to do 2 separate calculations to see how many moles of hydrochloric acid can we make. Okay? The limiting reagent is going to be the one that produces the smaller amount of product. Just like in our last example, our limiting reagent was hydrogen because it produced a fewer amount or smaller amount of ammonia molecules. Okay, so let's see how to do this. Here's our reaction again. And so we are going to do, like I said, 2 separate train tracks. We are going to do 1 train track with hydrogen and 1 train track with chlorine. And we're going to use both of them to figure out how much hydrochloric acid we can make. So our first one, we'll do hydrogen. Doesn't matter which one you do first. I just chose hydrogen. So we're going to start with the 4 moles of hydrogen that were given in the problem. And we need to figure out how many moles of hydrochloric acid we can make. Okay, so since we're going to change compounds, we're going to need to use that mole ratio. We're already in moles, so we can just go ahead and use the mole ratio right away. So looking at this, right, this is already balanced. We don't have a coefficient in front of hydrogen, so that's going to be just 1 mole of H2. We do have a coefficient in front of hydrochloric acid though, so we'll put 2 moles of HCl on the top. Now we make sure our units cancel. And we notice we found moles of hydrochloric acid, which is what we're looking for. So we can go ahead and do our calculation now. And if hydrogen was limiting, we would get 8 moles of hydrochloric acid. Now we are going to do this exact same calculation, but instead of starting with hydrogen, we're going to start with chlorine. So the problem said we have 2 moles of chlorine. All right, so again, we need to figure out how many moles of hydrochloric acid, so we're going to need to change compounds. We are already in moles, so we can go ahead and use the mole ratio right away. So again, there's no coefficient in front of chlorine, so that'll be 1 mole of Cl2, and we'll put 2 moles of HCl on the top. So again, in both of these, we are trying to find out moles of HCl. We just have a different amount of starting material. So we'll make sure our units cancel and get our answer. So now this calculation, this bottom one, that assumed chlorine was limiting. So each one of these calculations assumes one of our reactants is our limiting reagent. The actual one that's the limiting reagent will produce the smaller amount of product. So since chlorine produced a smaller amount of hydrochloric acid, therefore chlorine is going to be our limiting reagent, okay, because it produced a smaller amount of product. So that means that we'll use up all of our chlorine and we can't make any more hydrochloric acid. We can do the same calculation using grams, okay? Like we were talking about last time, most of our calculations in chemistry start and end with grams because we are going to weigh them on a balance. we can't weigh things out in moles, so while the last calculation was really simple and straightforward, that's not usually how it plays out in lab because we have to measure things out in grams. So here's an example problem. This says calculate the mass of water produced when 8 grams of hydrogen and 24 grams of oxygen react. Again, we're going to need to have a chemical equation because we need to see the mole ratio between hydrogen and water and oxygen and water. So the first thing we'll do is we'll write a balanced chemical equation. Again, this is a combination reaction, and you should be able to write this reaction from our work in Chapter 10. If you're still a little bit shaky on that, you do have time to go through and do some more of those lecture worksheet problems to make sure you're really solid on writing balanced chemical equations. All right, let's move forward with this. So again, do you see that we're given 2 different amounts of starting material? We're given an amount of hydrogen and we're given an amount of oxygen, and we want to know how much water. Okay, so again, since we have 2 different amounts of our starting material, we are going to make 2 different train tracks. And for each one, we're going to calculate grams of water. So let's do it for hydrogen first. We're going to start with our 8 grams of hydrogen. Okay, in the long run, we're trying to find out information about water, and we're starting with hydrogen. That means we are going to need to change compounds. Anytime we change compounds, we have to go through moles. So our first step here is going to be to turn our grams into moles. And the way that we do that is we use the molar mass. So the molar mass of hydrogen will go on the bottom, and that will be equal to 1 mole. Remember, our molar mass is always equal to 1 mole. And so when things are equal, they get stacked. Make sure you're not putting any other numbers other than 1 anytime you're using the molar mass. All right, so doing that turns our grams into moles, and now we can use the mole ratio to change moles of hydrogen into moles of water. So our coefficient for hydrogen is 2, so 2 moles of water will go on the bottom. And then our coefficient 2 moles of hydrogen will go on the bottom. Our coefficient for water is also 2, so 2 moles of water will go on the top. Make sure our units cancel. And then you'll notice that our problem is asking for the mass of water. Therefore, we need to convert these moles of water into grams. The way that we do that is by using the molar mass. So 1 mole of water will give us 18.02 grams, and we can make sure all our units cancel and get our answer. We are going to do this exact same problem, but instead of starting with hydrogen, now we're going to start with our oxygen. Okay? So when we start with our oxygen, we'll start with 24 grams of oxygen. And again, like I said, you're going to do the exact same process, just now you're using oxygen instead of hydrogen. So we'll use our molar mass to change our grams of oxygen into moles of oxygen. Once we change it into moles of oxygen, now we can use our mole ratio to change moles of oxygen into moles of water. There's no coefficient in front of oxygen, so it's just 1 mole. And then we have our 2 moles of water on the top. The end of this train track is actually going to be the exact same as the one above it, because in both of them, we're trying to change our moles of water into grams of water by using the molar mass. So once we get our answer, now we are going to compare them. It says calculate the mass of water produced. In order to calculate the mass of water produced, we need to take into account the limiting reagent. So do you see that the one on the bottom, the oxygen, is producing a smaller amount of water? That's telling you that oxygen is our limiting reagent. Okay? The one that produces the smaller amount of product is going to be our limiting reagent. So oxygen here is our limiting reagent. Since oxygen here is our limiting reagent, that means the maximum amount of product that can be formed is 27 grams of water. We can't produce 71.5 grams of water because we will run out of oxygen before we get there. We are always limited by our limiting reagent, so that means the actual mass of water that's produced here is going to be 27 grams of water. Okay? So again, oxygen is our limiting reagent and hydrogen is our reagent in excess. All right, I want you to try one. This says calculate the mass of carbon dioxide produced when 12 grams of carbon monoxide and 9 grams of oxygen react. I was so nice, I've already provided you with the balanced chemical equation. Now what you need to do is make your two separate train tracks and figure out the mass of carbon dioxide that can be produced from this reaction. So go ahead, pause here, try this out, and then come back when you're ready to see the answer. Alrighty, so again, we're going to need to make two separate train tracks. One with the carbon monoxide to see how much carbon dioxide we can make, and the other one with oxygen to see how much carbon dioxide we can make. We then will compare those two answers, and the one that makes the smaller amount is the mass that will actually be produced. So let's go through this. If we assume that carbon monoxide is limiting, then we'll start with our 12 grams of carbon monoxide. We know we're going to have to change compounds, right? We're going to have to find out information about carbon dioxide. So in order to do that, we need to change compounds, which means we need to be in moles. We're not in moles right now, so we're going to use our molar mass to turn grams into moles. So our molar mass will go on the bottom because grams has to cancel grams, and 1 mole will go on the top. Once we've turned this into moles, now we can use our mole ratio to turn moles of carbon monoxide into moles of carbon dioxide. So if we look at our coefficients, the coefficient in front of carbon monoxide is 2, and so is the coefficient in front of carbon dioxide. So we'll make sure our units cancel again. And now our problem is asking for the mass of carbon dioxide. So we'll use the molar mass of carbon dioxide to turn moles into grams. So 1 mole of carbon dioxide will go on the bottom, and our molar mass will go on the top. Make sure our units cancel, and we'll get our answer. We will do this exact same process now, but now we're going to be starting with oxygen. Okay, so we say, okay, if instead oxygen's our limiting reagent, how many grams of carbon dioxide can we form? So we'll start with our grams. Again, our first step will always be to turn grams into moles using the molar mass. Remember, we can only change compounds by using the mole ratio, which means we need to have moles. Now when we do this though, our coefficient in front of oxygen is a 1. So we only have 1 mole of oxygen for 2 moles of carbon dioxide. And then our very last step is to turn our moles of carbon dioxide into grams of carbon dioxide using the molar mass. All right, so now we're going to look at these two numbers. Remember, this first calculation was assuming carbon monoxide was limiting, and the second one was assuming oxygen was limiting. Since our top one produced a smaller amount of carbon dioxide, that's the actual mass of carbon dioxide that will be formed. That is our answer to this problem, not this one. We can't make 24.8 grams of carbon dioxide because we will run out of carbon monoxide. That means that our carbon monoxide is our limiting reagent and our oxygen is our excess reagent. Okay? All right, so this problem is probably the trickiest problem in Chapter 11, in my opinion. So if you're a bit confused, know that this is more of a challenge problem than anything else, okay? It may show up on a quiz or a test, but it is going to be the trickiest type of problem in Chapter 11. So this is going to be calculating the amount of the excess reagent left after the reaction. So remember, the limiting reagent gets totally used up in our chemical reaction, but there's going to be some of our excess reagent left over. Again, if you think about like drawing those stick figures, we had leftover arms and legs and torsos. So this is kind of telling us how many arms and legs and torsos are left after our reaction happens. How much of our excess reagent is left, okay? So this says how many grams of silver bromide can be produced from 50 grams of magnesium bromide and 100 grams of silver nitrate. That's essentially what we've already been doing. This is the amount, right? That's one of our starting materials, magnesium bromide, and 100 grams of silver nitrate is our other reagent, right? So those are here, 2 different amounts of reactants, and I want to know how much product we can make. That's what we've been doing already. The new thing, though, is this problem. How much of the excess reactant remains? And again, that's a bit tricky. So I'm going to try and explain it to you as best I can. You're going to have to kind of conceptually think about this though to really get a handle on it. All right, so let's answer the first question first because we already know how to do that. This says how many grams of silver bromide can be produced from 50 grams of magnesium bromide and 100 grams of silver nitrate. So again, we're going to make two separate train tracks, and in each one of them, we are going to figure out how many grams of silver bromide we can make. So let's do that first. We start with our 50 grams of magnesium bromide, and again, every time we have grams, we're going to need to turn that into moles using the molar mass before we can change compounds. So we'll use the molar mass of magnesium bromide and 1 mole of magnesium bromide to turn grams into moles. Once we've done that, now we can use the mole ratio to turn moles of magnesium bromide into moles of silver bromide. You'll notice there's only 1 mole of magnesium bromide in our balanced chemical equation, but there's a 2 in front of silver bromide, so we put a 2 here. Okay. Now that we have moles of silver bromide, we can use the molar mass of silver bromide to convert moles into grams. So 1 mole will go on the bottom, and our molar mass will go on the top. Now we can multiply everything out and get our answer. Now we're going to do the exact same calculation, but we're going to start with silver nitrate instead of magnesium bromide. So we'll start with our 100 grams of silver nitrate, and we'll use the molar mass to turn grams of silver nitrate into moles of silver nitrate. Once we're in moles, now we can use the mole ratio to turn moles of silver nitrate into moles of silver bromide. So if you look at our balanced chemical equation, for every 2 moles of silver nitrate, we're going to get 2 moles of silver bromide. And then once we have moles of silver bromide, we can use the molar mass to convert moles into grams. Then we'll multiply everything out and get our answer. So just like we've done before, we'll go ahead and compare these two amounts and figure out how many grams of silver bromide can be produced. Remember, the actual answer is always going to be the one that is smaller. So here, the actual amount that we can produce is 102 grams of silver bromide. That's telling us that our magnesium bromide is our limiting reagent and our silver nitrate is in excess. Okay, but when it asks how many grams, this is your answer. This is telling you, okay, I can make 102 grams of silver bromide. Remember, we can't make 110.3 grams because we will run out of magnesium bromide before we get there. Okay, so here's our actual answer, 102 grams. All right, so now we need to figure out how to deal with this second question, right? How much excess reactant remains? So the way that we do that is we figure out how much silver nitrate is actually going to react with the limiting reagent, okay? So we're going to see, okay, if we start with our 50 grams of magnesium bromide, how much silver nitrate reacts with that? Okay, so we're going to start a train track here with our limiting reagent, and we're going to figure out how many grams of our excess reagent react with it. So we're going to start with our 50 grams of magnesium bromide, and we're going to turn grams into moles using the molar mass just like we've done before. But now, instead of trying to figure out how much product, we are figuring out how much of our excess reagent we need to react with our limiting reagent. So we're going to say, okay, for every 1 mole of magnesium bromide, we are using up 2 moles of silver nitrate. And then again, since we weigh things in class in grams, we need to convert our moles of silver nitrate into grams of silver nitrate using the molar mass. So here again, in this calculation, we are figuring out, okay, if we start with our limiting reagent, how much of our excess reagent is actually going to react. Once we do that, we can figure out our amount that's going to be left over. The calculation here is going to be, okay, how much did we actually start with? Our initial amount. That's going to be given in the problem. So we started with 100 grams of silver nitrate at the beginning. We're going to subtract out the amount that actually reacted. That's here. That's what we were calculating. The amount of our excess reagent that actually reacted. So 92.3 grams of silver nitrate actually reacted. So we'll subtract that out. So if we do 100, the amount that we started with, minus 92.3, the amount that actually reacted, we'll get how much is still floating around in solution unused. Okay, so again, I think this is a tricky calculation because you need to have gone through and already figured out the limiting reagent. Usually you'll do that anyways because I'll typically ask how much product you can form, so you're going to need to make those two train checks anyways and figure out which one's the limiting reagent and all of that. This, though, is going to say, okay, we're going to start with our limiting reagent, figure out how much of our excess reagent reacts, and then do initial minus the amount reacted to figure out how much is left. Again, this is the trickiest calculation in Chapter 11, so I do want you to get some practice on it. We are going to get some practice by completing page 3 of the limiting reagents worksheet. So back to that worksheet we were working on earlier, we're going to keep going. So here is a problem similar to the one that we were just doing. This says if we have 10.02 grams of hydrogen and we mix it with 28.02 grams of nitrogen and we're forming ammonia, I want to know which reactant is the limiting reagent. Okay, so in order to answer that first question, again, you're going to need to make two different train tracks, one for hydrogen, one for nitrogen, and figure out how much ammonia you can make. That will also help you answer number 2, where it says how many grams of ammonia could be produced by that reaction. Remember, the one that produces less is the one that's our actual amount that's being produced. And then number 3 says how many grams of the excess reactant were actually used in that reaction. So for that one, you are going to take our limiting reagent and you're going to figure out how much of our excess reagent actually reacted. Then you're going to answer number 4, and it says how many grams of the excess reactant were left over. Remember, that one you're going to do initial minus the amount reacted to get the amount left over. All right, go ahead and pause here and try this out, and then come back when you're ready to see the answer. Alrighty, so in this first one, like I said, you are going to need to make two separate train tracks, one for hydrogen and one for nitrogen. So for hydrogen, we're going to change our grams into moles using the molar mass just like we did before, and then we're going to use the mole ratio, that's that step here, which says for every 3 moles of hydrogen, we're going to make 2 moles of ammonia. And then we'll use the molar mass to turn our moles of ammonia into grams of ammonia. We'll do the exact same thing for nitrogen. So we'll start with our nitrogen. We'll use our molar mass to turn grams into moles. And then again, we'll use our mole ratio from the balanced chemical equation to turn our moles of nitrogen into moles of ammonia. And then you'll use the molar mass again to turn moles into grams. So we'll compare these two numbers. Since 34.08 grams of ammonia is smaller, that means that nitrogen was our limiting reagent because it produces less ammonia. This 34.08 becomes our answer for number 2. Remember, the one that is smaller out of these two train tracks, that's the amount that's actually produced. We can't make 56.4 grams of ammonia because we would run out of nitrogen. Number 3 says, okay, how many grams of the excess reactant were actually used in the reaction? So we're going to take our limiting reagent and we're going to put that here. So we're going to take our 28.02 grams, that's our amount of nitrogen. We're going to start with that and we're going to figure out how many grams of hydrogen actually react. So again, we'll use our molar mass to turn grams into moles. And then we'll use our mole ratio again here to turn moles of nitrogen into moles of hydrogen. Then we can use the molar mass of hydrogen to turn moles into grams. So this is the amount that actually reacted. We started with 10.02 grams of hydrogen, but we only used up 6.048. So when it asks how many grams were left over, we're just going to subtract those two amounts, and we'll get that we have 3.97 grams of hydrogen in excess. All right, let's try one more. So this is similar to the last problem, except you'll notice in the last problem, I broke it up into a bunch of different pieces for you. Instead of breaking it up into a bunch of different kind of sub-questions, I've just given it all in one go. This says 64 grams of ammonia are mixed with 64 grams of oxygen to produce nitrogen monoxide and water. Here's our balanced chemical equation, and I want to know which reactant is the limiting reactant. How many grams of nitrogen monoxide could be produced in this reaction, and how many grams of the excess reactant would be left over. So this is essentially the same as what we were doing before. I just haven't broken it down kind of and given you space to do it. You'll need to figure out, how much space you need and what train tracks you need to make to figure out your answers. So go ahead, pause here, try this out, and then come back when you're ready to see the answer. Alrighty, let's go over this. So in order to figure out the limiting reagent, we need to do our two separate train tracks, just like we've been doing before. So with one of them, we're going to start with our 64 grams of ammonia, and the other one, we are going to start with our 64 grams of oxygen. So two separate train tracks. So for the first one, we'll take our grams of ammonia, we'll use our molar mass to turn it into moles, and then we'll use our mole ratio. So for every 4 moles of ammonia, we are making 4 moles of nitrogen monoxide. And then we'll use the molar mass of nitrogen monoxide to figure out our grams. Okay, we'll do the exact same thing for oxygen. We'll use the molar mass of oxygen to turn it into moles, mole ratio to turn it into moles of nitrogen monoxide, and then we'll use the molar mass to turn it into grams. We'll compare those two numbers and we see that this one, right, 48 grams of nitrogen monoxide is a smaller amount. Therefore, oxygen is our limiting reagent, okay? Remember, when we see the smaller amount, that's the amount that will actually be produced. So when it says for part B, how many grams of nitrogen monoxide could be produced, it's always going to be the smaller one. We can't make 110 grams because we would run out of oxygen. All right, so number C, like I said, is the trickiest type of calculation in my opinion. And it says how many grams of the excess reagent would be left over. Okay, so what we're going to do is we're going to take our limiting reagent and we're going to start a new train track with it. That's 64 grams. But instead of forming product, now we are going to figure out how much of our excess reagent actually reacts. So again, we're going to use use our molar mass to turn grams into moles. We'll use our mole ratio to change compounds, but again, now we're trying to figure out the excess reagent. Then we're going to use moles and our molar mass to turn it into grams. So this says that we had 27 grams of ammonia that were actually used. So if we started with 64 grams of ammonia and we actually used 27, that means we have 37 grams of ammonia in excess, or we have 37 grams left over. Alrighty, switching gears onto a new topic. One of the major topics in chemistry, or one of the major calculations that we do in a chemistry lab, is we figure out our percent yield. The percent yield is super useful because it tells us how well our reaction went. Did we spill things along the way? Did we forget to dry it? Did the reaction go to completion? All of these different things are all contained in the percent yield. So this, again, is a very important lab-based calculation. But let's get some definitions out of the way. The first one is our theoretical yield. So our theoretical yield is essentially on paper, doing calculations, doing these train tracks. So in theory, how much product can we actually make? This will be determined using the balanced chemical equation, mole ratios, stoichiometry, all of that. So I like to think about this as in theory, right, or on paper. Right? This is not essentially taking into account, okay, I tripped and spilled, or I knocked it over, my lab partner did this, whatever, right? This is in theory. If it went perfectly, how much product can we make? Our actual yield is what we actually get in the lab. So that'll be the amount of product that we get from actually doing an experiment. Okay, this is sometimes also called the experimental yield because, again, it comes from doing an experiment. This actual yield is typically lower than our theoretical yield because, again, things happen, right? Some powder spilled on the table or whatever the case may be. The actual yield is typically smaller. Our percent yield is a way of comparing the actual and theoretical yield, and it's a really simple calculation. The percent yield is the actual yield over the theoretical yield times 100. So we just look at the ratio of these and give us a percent yield. So obviously 100% yield would be everything went absolutely perfectly. Not a single drop was spilled along the way. You guys have been in lab for a while. You know this is not usually how it plays out, right? Usually things happen. So typically our percent yield is lower than 100. Sometimes it can be higher than 100, and this is usually if our product that we're making is still a little bit wet. Remember, we learned how to dry things to constant mass to make sure that all of the water was off of our product. This is really important for calculating percent yield because if you still have some water on there, your mass is going to seem too high and you're going to get a percent yield over 100, which is not possible. All right, so let's do some practice calculating percent yield. In order to calculate percent yield, we need to have both the actual yield and the theoretical yield because we're going to divide them up and multiply by 100. So here's an example. Let's say we were making cookie dough and we were going to make 5 dozen cookies. Doesn't that sound delightful? Some like lovely chocolate chip cookies. But while you're making it, the phone rings and you have to answer it. Let's say it's your mom and you have to answer it. While talking, a sheet of 12 cookies burn tragically and you have to throw them out. Like they're not like a little bit burned. It's like burnt to a crisp. They're black. Okay. Rest of the cookies are okay though. So what is the percent yield of edible cookies? All right. So thinking about this, we were trying to make 5 dozen cookies. That was the goal. So in theory, on paper, we were going to make 5 dozen cookies. Remember, a dozen is 12. So 5 times 12 gets us 60 cookies that we should have had. However, 12 of our cookies burned, which means we didn't make 60 cookies. We actually made 48 cookies. Super bummer. Okay, so 60 would be our theoretical yield. In theory, on paper, we should have had 60 cookies. But as you know, stuff in lab happens, and we only ended up with 48 cookies. So our percent yield would be our 48 cookies, right? Our actual yield divided by our 60 cookies, our theoretical yield, and then multiplied by 100. So we got an 80% yield. Overall, if we were in lab, 80% yield, not bad. In terms of cookies, I would be super bummed if we lost 12 cookies. Alrighty, let's go back to chemistry. So this says without proper ventilation and limited oxygen, the reaction of carbon and oxygen will produce carbon monoxide. All right, so again, we always need to have a balanced chemical equation. This is key for pretty much everything in chemistry. So if I haven't given it to you, you're going to need to be able to write one. This says what is the percent yield if 40 grams of carbon monoxide are produced when 30 grams of oxygen are used? All right, so looking at this, do you see that we have 2 masses again? This looks kind of similar to the problems we were doing before, right? We were doing limiting reagent problems and we had 2 masses and we made 2 train tracks. So how do we know whether it's a limiting reagent problem like we saw before or a percent yield problem like this one is? In a limiting reagent problem, you will be given amounts of 2 starting materials, 2 of your reactants. That would be a limiting reagent problem because in both of those, you would make a train track to figure out how much of your product you're making. 1 train track for each of your reagents. Here, this says we have carbon monoxide and oxygen. Okay, so do you see now we're given amount of a reactant and of our product. So this is different. In a limiting reagent problem, you will only be given amounts of your starting material. In a percent yield problem, you will be given an amount of your starting material and an amount of your product. So the amount of your product is going to be an actual yield. Do you see it says are produced? This is going to be your actual yield. And you will do some math to figure out your theoretical yield from oxygen. So we're going to use this to find the theoretical yield. Okay, so we're going to do a quick train track with our oxygen to figure out, in theory, if it went perfectly, how much of our carbon monoxide could we make, because this is our actual yield. Then we can compare our theoretical yield and our actual yield to get the percent yield. So let's go through this. Okay, so to find the theoretical yield of carbon monoxide, we are going to take that mass of oxygen that was given to us. And again, our theoretical yield is always going to be determined from stoichiometry. It's always going to be determined by a train track. Okay, because that's saying, in theory, on paper, if everything went perfectly, how much could we make? So we're very familiar with this calculation by now. We're going to use the molar mass of oxygen to turn grams into moles, just like we've done before. And then we'll use our mole ratio to turn moles of oxygen into moles of carbon monoxide. In our balanced chemical equation, we see that there's only 1 mole of oxygen for 2 moles of carbon monoxide. So we have that there. And then we can use the molar mass of carbon monoxide to turn moles into grams. So multiply all that out and we'll get our answer. So that is the theoretical yield of carbon monoxide. Again, our theoretical yield is always going to be from a train track. Now we can calculate the percent yield because the actual yield was given in the problem. Our actual yield, it said, was 40 grams of carbon monoxide. So we did this reaction, we only got 40 grams. In theory, we should have gotten 52.5 grams, but like we've said before, stuff happens and you lost some, okay? So in order to calculate our percent yield, it's always actual over theoretical times 100. So we get a 76.2 yield. It's not bad, right? It's not like awesome, but it's not bad. Alrighty, your turn for a practice problem. This says when nitrogen and hydrogen are mixed, the reaction produces 16.0 grams of ammonia. What is the percent yield of the reaction? And just for fun, I'm going to leave off the balanced chemical equation so that you can get some practice doing it. So the very first thing you need to do is write the balanced chemical equation. And then again, you'll notice that this is a percent yield problem because we are given a mass of a reagent, right? A mass of a starting material and a mass of our product. So this is different from a limiting reagent problem when we're only given masses of our reactants. All right, go ahead and pause here, see if you can figure out the percent yield, and then come back when you're ready to see the answer. Alrighty, here's our balanced chemical equation. So again, you should have done that first. So we have nitrogen plus hydrogen are giving ammonia, and you need to go through and balance it. The key here was balancing those hydrogens to 6 so that we get a balanced chemical equation. Alrighty, so let's calculate the our theoretical yield, of ammonia. The first thing we'll need to do is take the mass of our starting material and turn that into grams of ammonia. Remember, our theoretical yield is always going to be, in theory, on paper, if everything went perfectly. So we'll use our grams of hydrogen and we'll use the molar mass to turn grams into moles. Once we have our moles of hydrogen, now we can use the mole ratio from the balanced chemical equation to turn moles of hydrogen into moles of ammonia. Then we can use the molar mass to turn moles of ammonia into grams of ammonia. And then we'll get our answer. Okay, so that's the theoretical yield. In theory, on paper, if everything went perfectly, that's how much ammonia we could make. But we didn't. We only made 16 grams of ammonia versus, we should have made 28.2. So we'll divide those up and multiply by 100 to get our percent yield. Not a great percent yield, 56.7. I wouldn't be super impressed. Okay, but again, we're always going to put actual over theoretical times 100 to get our percent yield. Alrighty, we have reached the end of today's lecture. So I want you to work on problems number 26 to 32 on the Chapter 11 lecture worksheet. I know we covered a lot of ground today. We learned how to do limiting reagent problems and percent yield problems. we got a ton of practice with stoichiometry, especially the grams to grams stoichiometry, because like I said, that has practical applications in lab. So for me as a chemist, these calculations are super important, probably one of the most important topics in chemistry, because they allow us to do calculations in lab and do reactions in lab. The percent yield calculation allows us to figure out how well our reaction went. Did we spill a bunch along the way and get a really low percent yield, or did we totally rock it out and get almost 100% yield? Okay, so again, I like this chapter because it is very, very, very practical. So I know this is a math-based chapter, so make sure you are getting a lot of practice with these problems. Like, do the lecture worksheet and then print it out and do it again if you need to. Really, really, really nail down these calculations. If you need help, though, please reach out to me. I am more than happy to help. I really like this stuff. It's one of my passions, so make sure you reach out if you need anything. But otherwise, keep working hard, and I'll talk to you guys next time.